All right. What we have here is we are doing a application problem dealing with integration, fundamental theorem of calculus, and understanding how velocity, speed, and all these other things, distance and whatnot, apply to a certain graph. Okay, so what we have here is we have f. It's a differentiable function whose graph is shown in the figure, which is right here. The position at time ts of a particle moving along a coordinate axis is given by this integral. So s of x is equal to the integral from 0 to x of f of t dt. All right, and that's in meters. Use the graph to answer the given questions, give reasons for your answers. All right, so in this, what we have is we have this graph, okay? And this right here is given in the equation for s. Now, whenever you're given this equation, you have to understand what is everything representing. Well, s is distance. So s of x is going to be distance, okay? Or you could say displacement, if you want to say it that way. Displacement, probably a better term. And displacement means that there is going to be both a direction in for where we are moving. Okay, so when to get distance, there's going to be more displacement. Okay, so it's going to be a positive, negative direction, or negative direction. All right. Now the next thing is, whenever I deal with distance, time function, all that stuff, I want to try to figure out what is velocity and all this, because that's eventually going to be coming into the problem. So we know that the derivative of s of x, the derivative of s, is going to equal velocity. Okay, velocity of x. Okay, so that's the velocity. Now, if you take the derivative of s, you realize that this s is actually this integral, the integral. So that means when we take the derivative of the integral, if you recall from the fundamental theorem of calculus, the derivative of this integral actually equals the function, okay? Because you take the antiderivative, then you take the derivative of the antiderivative, and you get back to the function that you integrated, all right? The integrand inside. So the derivative of s actually will equal the derivative, all right, of the integral, which will then equal f of x. All right, so all I have to really say is the velocity, which is the derivative of s, is equal to f. All right, so that's important. The next thing is, if we know anything about this, we know that the second derivative, which is the first derivative of velocity, which then will equal acceleration, is equal to, all right, the derivative of f. Okay, so acceleration, we know is going to be the derivative of f, the slopes of that curve. Okay, so now we're ready to answer some problems. Okay, so I have some problems down here, and let's see how we can do with them. All right, what is the particle's velocity at time t equals 5? All right, when plug in 5 in for t. Okay, and actually probably should maybe switch this up. I think I wrote this wrong, I apologize. So we'll put t and we'll put x in there, and we'll put x right there. All right, we'll put t there, and t there, and t there. All right, and t there, and t there, and x there, and t there. Okay, so we're just going to switch some things up right there. But we're going to have t, okay? So now, when we have this, when time t equals 5, okay, so we're going to plug in 5 into here. Well, what is velocity? Well, velocity we know if we're trying to find v of 5, okay, v of 5, we understand that's going to be s prime of 5, which equals, in this case, we just wrote out, it should be equal f of 5. So, to figure out f of 5, all we're going to do is, this is a graph of f of 5, which is the velocity function. All right, this is the velocity. All right, velocity function. So, what is the velocity at 5? Well, it's just a value, which will equal 2. All right, we know 2. All right, so it's going 2 meters. I don't know if it is seconds. Yep, 2 meters per second. All right, 2 meters per second is going to be the velocity of this function because the function itself is the velocity of s. Is the acceleration of a particle at time t equal 5 positive or negative? Well, to figure this out, the acceleration is the slope of the curve. All right, and if you look at this curve right here, all right, so acceleration actually is the derivative of velocity, which actually would be the derivative, all right, of f. Well, what's happening at 5? Well, you see that it is decreasing, all right, so f is decreasing, all right, f is decreasing, all right, therefore, all right, that means that f prime would be negative or less than 0, all right, and since f prime equals acceleration, which we said over here, we know the acceleration should be negative. All right, then acceleration, right, is negative. All right, and that's how we can identify that right there. Okay, acceleration is f prime, f is decreasing, f prime then has to be less than 0. All right, and then the acceleration is negative. Okay, we'll continue on. What is a particle's position at time t equals 3? All right, particle's position. Well, position refers to s. So we're trying to find s of 3. So to find s of 3, we're going to look at our original function. S of 3 is this. All right, is the integral. That's really important. So what we're going to do is we're going to take the integral from 0 to 3 of f of t, or f of x dx. All right, and that is going to give us s of 3. Now, from here, we understand that 0, all right, if we integrate from 0 to 0, our initial position, it doesn't say it is anywhere, so we're going to assume that this initial position is going to be 0, so it starts at 0. So in order to just figure this out, all we're going to do is find the integral from 0, it appears, from 0 to 3. Well, to find the integral from 0 to 3, given a graph, we're actually going to find the area underneath the curve. So starting at 0, we can go to 3, it's right here, and if you recall, well, what kind of area is this? Well, it's not really a curve, it appears to be just a straight line, all right, and what we have is a triangle. All right, so we're going to try to find the area of this triangle, and the area of this triangle is going to give us the integral. Well, what do we have here? Well, the area of this triangle is 1/2, the base, which appears to be 3, times the height, which is also 3. So what we have here is the position appears to be 9/2. All right, 9/2, that's going to be in meters, all right, and that is where we're located at time equals 3. Well, continuing on, all right, at what time during the first 9 seconds does S have its largest value? Largest value. All right, well, largest value, we're looking for S, so once again, we're looking for position. So where is it the largest positive value? Well, we know that S of 0, if we integrate this from 0 to 0 of f of x dx, all right, is going to equal 0. Okay, so that means if we look at our graph right here, okay, looking back over here, okay, once again, we're finding area. Okay, S is going to be finding area because this is our velocity. Well, we're starting here, if you kind of think about it, we're starting at 0, and what happens is our velocity is positive, so what happens is it keeps on increasing. All right, so that means S is increasing. Well, it keeps on getting larger and larger, and you notice that we have this positive area all under here, and it keeps on going and going. It's still increasing, it's still positive increasing, until we come to this point right here, which is 6. At 6, we realize that the velocity starts to become negative, all right, and then it begins to decrease. Well, since, all right, S prime is changing from, because remember, S prime is velocity. Since velocity changes from positive to a negative value, this actually would be the maximum value, or we have a positive, all right, largest value. So we know that the largest value, okay, at what time? Well, it appears to be when t equals 6 in this case, all right, 6 in this case. And the reason why that is the largest value is because that is the location where, all right, t changes from positive to negative, all right? So that's where x prime, which equals f, changes from positive to negative, all right? So t, all right, t equals 6 is the location of the largest value because, all right, because, all right, of this reason right here, S prime changing from positive to negative, and we're starting at 0, so that's going to be the largest value there. All right, next thing is we're going to try to figure out some other ones. Let's find these. When is our acceleration going to equal 0? When is our acceleration 0? Now, acceleration is 0, if you think about this. So we're trying to find when a is equal to 0. Well, a is equal to v prime. V is, we know, we said it up here, v, all right, equals f, and we say that acceleration equals f prime, so I guess we're going to just have that right there. So when does f prime equal to 0? So when does the slope equal to 0? All right, so if you look over here, when is our slopes equal to 0? All right, when is our slopes equal to 0? Well, it appears that right here we have a slope of 0 because that's a max. And it appears that we also have a 0 there. It also appears to be a max as well. Okay, that's what we have. So we have a max, it appears to be right there, at 4 and at 7. Okay, so when t equals 4 and when t equals 7, right? 4 and 7 are when the acceleration equals 0. And that's when f prime equals 0. When is the particle moving toward the origin? Okay, moving toward the origin. Toward the origin is when the velocity is going to be is going to actually be negative. Okay, it's going to be negative. So less than 0. The velocity we know is f. So we're looking for when it's moving toward. When is the velocity negative? All right, that's moving to the left. It's moving negative from 6 to 9, all right, 6 to 9, all right, so right here, all right, from 6 to 9 on that interval, all right, that's what we have there. When away from the origin, so that is when the velocity is positive, so that's when v is positive, that's moving to the right, okay, moving to the right, and when is that positive? Well, it appears from 0, all right, 0 to 6, and that's when it's moving to the right, so from 0 to 6. All right, then finally, on which side of the origins does a particle lie at time t equals 9? T equals 9. All right, now, when we have the origin, because that's where we're starting, okay, and we're trying to figure out where it's going to be when t equals 9. Well, it's going to be to the right, it's going to be to the right of it if it's going away from it farther, all right? And it's going to be to the left, it's going to be a negative, all right, negative displacement. Okay, so that's what we're trying to figure out here. All right, so which side? All right, so if S is positive, all right, at t equals 9, then it's going to be to the right. If S is negative, it's going to be to the left. So how do we figure this out? Well, let's look at our graph. And looking at here, I'm going to erase some of this. Okay, as we start here, we're going to look at 9 right here. Well, you see that this area, we're trying to find the integral. Essentially, we're finding the integral. All right, the area from 0 to 6 is positive, and this area is much greater than the area from 6 to 9, which is negative. All right, so in my negative area, this is my positive area. Okay, you can see that. I'll put this in a different color. Positive and then negative, because, all right, because the integral from 0 to 6 of f of t dt, f of x dx, f of x dx, that value is going to be positive, and the integral from 6 to 9 of f of x dx, we know that area is going to be negative, all right? And we can also see by looking at this that the integral from 0 to 6, or the absolute value of that, all right, so actually the just displacement, or actually total area of this is greater than the integral from 6 to 9 of f of x dx. Now, because the area which is right positive is greater than the area that's negative, well, guess what? Then, all right, at t equals 9, that value, all right, that integral from 0 to 9 of f of x dx, all right, is going to be positive, right, greater than 0. Because it's positive, then, all right, the particle is to the right of the origin. All right. Okay, so here's a little bit of a synopsis on doing this. So what we had to find out was figure out where do I have positive area, where do we have negative area or displacement. All right. Then we figured out which area is larger. Okay, the total area, which total area is larger, and we realized that the positive area is bigger than the negative area. And so when you add them together, all right, and doing this integral, this has to be positive. All right, and that's why it has to be to the right of the particle when we're doing this. All right. Well, this was a very long tutorial, but this is a very essential problem. It's one that you see a lot on AP tests, and it really helps you understand of how we can use integration in applying to velocity and distance and displacement and acceleration, and how you can use graphs to help you do this. So hopefully these questions and this explanation allows you to understand this a little bit better and do other problems. So good luck and God bless on the rest of your assignments.